Welcome to Growth and Money. So the idea here is compound interest assumes essentially that, so compound interest is based on the rate of change being directly proportional to the amount in the account. So we have the amount or savings. We'll call that S. We have S prime is equal to K times S. And we therefore get our standard formula that S of T is equal to some constant C times E to the KT, where K is the interest rate. Let's actually do the interest rate. So we have R times S and then CE to the RT. So the compound interest, the constant of proportionality is the interest rate. So again, you have likely seen that compound interest formula before. That S winds up being the principal we invest. Sorry, the C. So we get S of T is equal to the initial amount, S naught, E to the RT. So let's go ahead and take a basic example. Let's suppose that $50,000 is invested in an account at an annual 2% interest compounded continuously. How long will it take for the amount in the account to grow to 200,000? So essentially we have S of 0 is $50,000. We have R is 0.02. We could write out the IVP if we want. So we have S prime is equal to 0.02x with S of 0 equaling 50,000. And then we want to know what is, or at what time T do we grow to 200,000? So again, we already know our IVP has solution S of T is equal to 50,000, our initial investment, E to the 0.02 T. So we can set this equal to 200,000. So if 200,000 is 50,000 E to the 0.02 T, this becomes 4 as E to the 0.02 T. And we get that T is natural log of 4 divided by 0.02, better known as 69.3 approximately years. So if we just leave $50,000 in an account earning 2% interest compounded continuously, it would take 69.3 years more or less for that amount to quadruple to 200,000. Now let's modify this. Let's suppose that you just put in $5,000 to start at an annual 2% interest compounded continuously. And then let's say you invest an additional $50 per week. We want to know approximately how long will it take to reach $200,000. So we've modified our differential equation here. So we are adding a constant $50 times $50 per week times 52 weeks per year. Or we're adding, what is that? $2,600 per year. So this isn't going to be precise compound interest. We're looking at sort of at any given moment in time, you're adding money. So we're going to assume instead of per week that $2,600 is kind of being continuously added throughout the year, divided throughout the year. So we're going to assume that $2,600 per year is sort of being constantly added in very small increments. So it will not be a perfect calculation here because we are approximating instead of we're taking the per week and then kind of assuming that we're just sort of splitting that so it's being added continuously. But it will be a good approximation. Those of you that have done accounting are likely familiar with the formulas that involve geometric series. So you've probably seen this before if you've done accounting, and this formula will be a little different because it is an approximation. So our approximate model will therefore be we have whatever we have in the account, the rate of change. We'll add in that 2,600 per year. And then plus our interest rate is going to be 0.02. So we're looking at plus 0.02 times whatever is currently in the account. So this is our regular addition. This is our regular investment plus the compounding, so the compounding interest. And yeah, so this is for our rate of change. Oops. So from here then, we also have initial condition of S of 0. This time around was just 5,000. So we're only starting out with a $5,000 investment and then putting in 2,600 per year. So we can go ahead and solve the IVP. So we rearrange this. We're looking at S prime minus 0.02S is equal to 2,600. We start off with a homogeneous equation. So if for the homogeneous solution, we have S1 should be equal to e to the 0.02 t, right? If that right side were equal to 0, that would be our solution. And then from here, we can go ahead and do our variation of parameters. So assume S is equal to U times S1. We then have that U prime is equal to that right-hand side, 2,600, divided by S1, so divided by e to the 0.02 t, or U prime is equal to 2,600, e to the negative 0.02 t. Integrating, we get that U of t is equal to negative 2600 divided by 0.02 e to the negative 0.02t, and then plus c. 2600 divided by 0.02, we get 130,000. So this is u of t is equal to negative 130,000 e to the negative 0.02t plus c. So our general solution we had s of t is equal to S1 times u. So S of t is e to the 0.02t times negative 130,000 e to the negative 0.02t plus c. And we get S of t is equal to negative 130,000 plus c e to the 0.02t. So unlike the original compound interest problem where our solution just took that generic form, this one, because it is a non-homogeneous linear equation, we have a little extra added on. Now we'll solve the particular, so solve the IVP. We know that S of 0 is 5,000. Set that equal to negative 130,000 plus C e to the 0.02 times 0. This means that we have 135,000 is equal to C. And so we have our savings S of t is equal to negative 130,000 plus 135,000 e to the 0.02t. And then the question was, when will this reach 200,000? So how many years? Will it take to save $200,000? Well, we have 200,000. Is that equal to to negative 130,000 plus 135,000 e to the 0.02t. And solving that, we have 330,000 is equal to 135,000 e to the 0.02t, or 330,000 divided by 135,000 is equal to e to the 0.02t. This winds up giving us that t is equal to the natural log of 330,000 divided by 135,000, and then that whole thing divided by 0.02. And if we plug that into our calculator, we wind up getting, let's see, natural log of 330 divided by 135, and then divided by 0.02. We wind up getting 44.7 approximately. I need to update my screen one moment. So we wind up getting 44.7 approximately. So that's 44.7 years of putting in about 2,600 per year. Again, this is an approximation because our differential equation itself was an approximation up to the problem. So again, note, this is an approximation. since the differential equation itself, or since the model was an approximation. But it should be relatively accurate. Again, for those of you who have studied accounting, there are specific formulas for this. Typically, banks, you're not doing compounded continuously, you're doing compounded monthly. And so there is a specific formula you would use if you were, say, investing monthly while also gaining interest compounded monthly. But this model is convenient for finding an approximation.